Hi students, this is Unit 3, Video 3. We're going to be discussing the diagram on page 159 of your textbook. Again, just to help you with skills of looking at graphs, but also to explain the actual material to you. So this is the diagram. In your textbook it's entitled The Oxygen Hemoglobin Dissociation Curve. Let's first look at the axes again and then we'll discuss it. So horizontal axis, ignore the blue. This is partial pressure of oxygen in millimeters of mercury. Now remember in the introductory video, in video 1, I said that one of the textbook refers to atmospheres as the unit of pressure. The other unit of pressure, which could also be used as millimeters of mercury, millimeters, and then Hg is the chemical symbol for mercury. And it's because barometers measure with a tube of mercury that rises and falls, just like a thermometer has a strip of mercury or alcohol that rises and falls. Similar idea, but it's for pressure, air pressure. So millimeters of mercury is one of the measures of pressure, atmospheres is the other. Your textbook uses millimeters of mercury. And then the P, the O2 means we're talking about oxygen. The P means partial pressure, and that's because we could talk about air pressure. That's the pressure of the volume of all the gases in the room or at sea level or above in Joburg or whatever. Or you can talk about just the pressure of oxygen in the air and just the pressure of carbon dioxide. And now that would change depending on different factors, like if we're talking about pressure of oxygen in your body, in your lungs, there'd be more oxygen than in your tissues, which are using up oxygen. So this graph is actually talking about the pressure of oxygen in your body, actually more in your blood, as it leaves your lungs and goes to your tissues. So this is the pressure of oxygen in the air or in the lungs or in the blood. This side of the graph is talking about oxygen saturation of hemoglobin, and it's measured in percent, so that's 100%, that's 0%. So remember hemoglobin, or maybe you haven't learned that yet because you're about to start the unit. Hemoglobin is the molecule that in your red blood cells that carries oxygen, and it can hold, each hemoglobin molecule can hold 4 oxygen molecules, and there's stacks of hemoglobin in your red blood cells, so your red blood cells can hold millions of oxygen molecules. And we can calculate and look at how saturated the hemoglobin is. Is it full of oxygen? Could it hold more? Is it empty of oxygen? That's what we're measuring here. So if all the hemoglobin had no oxygen, then it would be at 0%. The saturation of hemoglobin would be at 0%. If every single hemoglobin molecule was completely full of hemoglobin, then we'd be at 100%. And if some of the hemoglobin have lost their oxygen, then we're dropping down in here. So this graph is going to relate the pressure of oxygen in the air or in your lungs in your body to how saturated the hemoglobin is. Because basically there's this amazing phenomenon we designed brilliantly to that with quite significant changes in pressure, there's only going to be a tiny change in the hemoglobin saturation, and then at the end, when you finally at very low percentage of partial pressure of oxygen, then the saturation of hemoglobin changes very drastically, and it's really useful, and I'll explain why. But let's first look at the graph. So when we're breathing pure oxygen, like if you're in hospital, like my gran was this weekend, and they give her oxygen to breathe, she's breathing pure oxygen. And that means her blood would be 100% saturated with hemoglobin. And so that means all her tissues are getting as much oxygen as they need. Doesn't matter that she's not breathing very deeply, she's not breathing in very well, she's getting all the oxygen she needs. And so her blood is full of oxygen, which is good. And then here's what's interesting. As you get down to your lungs, normal lungs have about a partial pressure of 80 millimeters of mercury, according to your textbook. See how the graph hardly drops at all. So when you're breathing ordinary not with breathing pure oxygen, you're not experiencing very much difference. Your hemoglobin isn't very much less saturated than when you're breathing pure oxygen. Maybe it's worth asking someone, like a doctor, if you know someone, why is it then useful to breathe pure oxygen? I don't know the answer to that, but anyway. So it doesn't drop very much. And if we go even further, it still doesn't drop very much. And so that's partly why it's useful if we go into a room where everyone's been breathing and there's less oxygen because they've breathed out carbon dioxide and they've breathed in all the oxygen. It's not like our hemoglobin is suddenly really unsaturated. The graph's pretty flat up there. It doesn't make much difference. Or if you're outside where there's lots of oxygen, you don't experience that much difference. Maybe it would even have an effect high altitude, low altitude, if there's a difference in oxygen up there. I don't know if there is, but that's why you can breathe just fine. Your body doesn't experience all that much difference at different altitudes. And then so we're talking about our lungs and the oxygen. In our lungs we've got a partial pressure of 80 millimeters of mercury. Our blood at that point would be pretty well saturated. And then as our blood moves away from our lungs towards tissues that need oxygen, it will move, the partial pressure of oxygen will move down here to 40. Now I noticed in the text in your textbook it refers to normal tissue has a partial pressure of 40 millimeters of mercury. In the diagram, in the textbook, your graph in your textbook, the arrow for tissues is at 20. I think we should trust the text, not the diagram. So I've corrected my diagram to have the arrow at 40. So at your tissues are using up oxygen, so there's less around. Because remember, they're doing cellular respiration, they're breaking apart food molecules using oxygen. That oxygen is now used up. So there's less oxygen around the tissues. So we've got a partial pressure of only 40 millimeters of mercury. And have a look, if we read up, we should hit about 70. Okay, that means that when your blood gets down to 40, your tissues where it's 40 millimeters of mercury, it dissociates, the oxygen dissociates from the hemoglobin, it becomes separate, and 30% of it is now free. It loses 30% of it, and that gives it to the tissues. So your tissues, which need the oxygen because they're down here at only 40 millimeters of mercury of oxygen, are receiving oxygen because your hemoglobin is dissociating from the oxygen and releasing quite a good amount. So your hemoglobin will still have 70% of its oxygen, but it's donated 30%. And now here's what's interesting. If our partial pressure of oxygen drops below 40, like if you're doing really heavy exercise, the dissociation drops percentage dissociation drops really, really fast. So if we went down, let's say to 30, if we read up the graph, it would suddenly be only at 30%. So that means when we need it, like when we're exercising really strongly, our hemoglobin dissociates an extra 40% of oxygen. That's amazing. Like we didn't really need it that much when we were just at ordinary tissues, so we only needed it to dissociate to 70%, so only lose 30% of its oxygen. But when we really need it, like when we're exercising really strongly, it donates another 40%. That's really awesome. And then if we desperately needed it, it would donate even further. So our body's really perfectly designed to cope with small changes in atmospheric pressure of oxygen. Like we're not going to suddenly dissociate up here because that would be really bad. Our hemoglobin suddenly doesn't want to carry oxygen anymore, even though there's a fair amount around in your room. It doesn't do that. The hemoglobin has quite a high affinity for oxygen, even when we have a fair changes in oxygen partial pressure. But then when we need the hemoglobin to dissociate from the oxygen, because we need the oxygen, it dissociates really well. So it's a perfectly designed curve. You're probably not going to be required to draw this in your exam, but you might be required to explain it. So make sure you understand that it drops sharply when it's needed, down there at 40 millimeters of mercury. I think that's it. Thank you.